Hello everybody, this is Mohammad Abdulaziz and this is the third tutorial for the Functional Data Structures course. Today I'll be working on the sheet number 3. So I will start now. Please, if you have any feedback on the way the tutorial is done or ways you think to be improved, please either email them to me or put them on the Piazza forum. So let me start with the first exercise now. So here we want to re-implement the function isin. So before I start that, I just want to note that when you're building your theory file, you have to import PHP demo, which is on the public repository of the course, and that was the same file that was used by Professor Nipkow for his lecture. Okay. So let me start. So we need so we have a function isin. Let me just show you what it is. And that function tests whether a given member belongs to a tree. So let's go there. So as you can see, the function here, if the tree is a leaf, if the given tree is a leaf, then the function returns false. Otherwise, it checks if the given member x is smaller than the current element, the root of the tree. If it is, then it goes to the left subtree. Otherwise, it goes to the side. If it is strictly greater, then it goes to the right subtree, and otherwise, it just returns to you true, which is the case when x and a are equal. So here, firstly, I just want to note that this would only work for trees that are for search trees, as in trees where the members are ordered. So, like the left subtree has members always smaller than the root, and the right subtree has members that are greater than the root. So what we want to do is basically take this function and remove one of the comparisons. In particular, we want to remove this second comparison and re-implement the function so that it works with one comparison. Okay. So the way. So if this is right, let me just write the signature first. And here is an alpha option. Okay. So here I'm adding an then the new function will take an extra argument, and that argument. Okay. So let me just show you on the paper what this is for, and why is it there. Okay. So for example, if we have a tree like that, so 1, 2, 3, okay. And if we're searching for the element number 2 in this tree, so using isin, the original function, you will start here at that root and then compare 2 to 2. So 2 is not strictly smaller than 2, and it's not strictly greater than 2. So we will just return true because 2 is equal to 2, which is right. The new suggestion is you only do one comparison. So you have another function isin2 that does only one comparison. Okay. And that one comparison is just the strictly smaller than or comparison. So basically, if you're given a 2, you would go here and then you compare it. Is it strictly smaller than the root? No, it isn't. So you just directly go to the right. But in this case, if we just do what I said, you go to the right and then you compare it to 3 again, and then you would say, oh, it's not strictly smaller than 3, and it's not. And so you go to the right, and then it's a leaf, and then it's going to be false. So what we want to do is to basically carry with us this 2 that we didn't compare with, so that when we reach a leaf, we don't miss that we have met this 2 before. That is the extra argument that isin2 takes. So isin2 takes the first argument is a tree, and the second argument is postponed comparison, and the third argument is just the member that you're looking for, x. Okay. So so that postponed comparison is a type of type alpha option as written in the Isabelle file. Okay, and what that means is that it's either none, which means that you don't have any postponed comparisons, or it is some A, which means that you have some postponed comparison. Okay, so now I will implement that function. So here we have isInt2 of a leaf, and given a postponed comparison value z. Okay, so as I was saying, when you reach a leaf, you check if you have postponed the comparison or not. And what that means is you see case z of none. So if you don't have anything postponed, then false. If you have something, some y, then you return x equals y. Okay, so that's the first case. Second case here is this one. So here I remove that. Okay, I remove this extra comparison that we didn't want, and then here change this to 2. And then now what is the postponed comparison? So firstly, the postponed, see here, isn't should be taking postponed comparison as well. What is that? So if it is so if you go to the left and you didn't postpone any comparison because you have done your comparison until now, but if you're going to the right, which is the other case, you will have postponed the comparison with A. Okay. Okay. So that is the postponed comparison here. And the reason we always take their most recent value is because these trees, we assume that these trees are ordered. So if you have postponed, for example, if you have postponed, let's say that this tree was like that. This is okay, and we're looking for 3 here. Okay, so if we're looking for 3, then you will not go in that direction, and then you go in this direction, but the postponed comparison will be with 2. Okay, and then we go here again, and then we will do. It's not strictly smaller, so we'll go to the right direction again. But the postponed comparison here should change to 3. And why is that? Because if you're already not. So let's say you postpone a comparison here, and then you postpone a second comparison. That means that you're greater than or equal to the second comparison that you postponed. And the second comparison, because the tree's order is also known to be strictly greater than the first comparison that you didn't postpone. So you can safely discard the earlier one. So let me continue that. So now the second question in the exercise is that we want to prove this lemma about the new function isInt2. Basically that it behaves exactly like it is in the original one. Okay, and the reason we have here none as the argument is because when you're at the beginning, you didn't miss any comparison. You didn't postpone any comparisons. So that's why you begin with none. Okay. So let's see. There seems to already be a problem. So we have a counterexample there. So I must have made a mistake in the definition. You see. Oh, yeah, that is the mistake. You should go to the right here. Okay, so now let me see if there's a counterexample you can use quick check to check for explicitly check for counterexamples, or nitpick also. This is another tool, but I'm pretty confident there isn't one. There isn't a counterexample. Okay, so because this function is defined as a primitive recursive function, we can just do the recursion on the tree directly, because the function's recursion patterns follow exactly those of the type of the tree. So we have a new subgoal, and the problem with the subgoal is that 8 new subgoals, and the problem with the first subgoal, for instance, is that we need to prove something about isIn2 called with a sum value, and while the induction hypothesis only talks about isIn2 called for a non-value. Okay, so we basically need a lemma like that one, but for sum, and then we should use this lemma here. So let us see there. We need the lemma that is of that form, but of course there must be some more assumptions, because you can't just say that you're postponing comparisons with an arbitrary element. So for instance, okay, so this is a counterexample there that was found. So what I usually, so here we have an empty tree, and like the postponed comparison is A1, and X is also A1. So basically, if you say that if you apply this function to an empty tree with the postponed comparison of the same element that you're looking for, you will get a true, even though isIn, the traditional one, will give you a false, because the X is not in the tree. So what we want to say is that this is equal isIn X, T or X, T and X, or Y or A equals X. Okay, so that's one thing. Let's see if there are counterexamples. So there is another counterexample, but this one is not clear because here we have an A1 and an A2, and it's not clear to me which one is greater than 1. So in order for me to make the counterexample more readable, I'll just make these trees of natural numbers, so not tree, and then look at the counterexample now. So basically here, the counterexample is that you have a tree whose member is whose root node is 0, and you postpone your comparison with a 1, and X is a 1. Okay, so so in this case, again, we will get a true from isIn2, but a false from isIn, and sorry, we'll get a false from isIn2 and a true from this disjunction, because A is the same as X, even though that will give us false. Okay, so we need to assume also another assumption that actually should have come from there, is that the postponed comparison is always smaller than every member in the given tree. I think that's why we have this counterexample there. If we assume that, then this one will be less than 0. So let's just add that assumption. So basically what we want is another assumption that says I'll just copy it from there and change it. So everything in the tree is strictly greater than the postponed comparison. So let's see if we have the counterexample again. Okay. Okay, so I think this is the right lemma now. So let us prove it by induction again on the tree and auto. Seems like it's not going through. Okay, so it's not going through because the induction hypothesis here talks about ising 2 applied to tree number 2, but with a specific value for the postponed comparison, while in the conclusion we have another value which is x2. So we need to generalize again. So here we can do this generalization either by quantifying over a like that and see what happens. So now the sub goal is done, yeah? Or instead of quantifying and saying for all a, you can also do it by saying arbitrary a. It's the same, yeah. Okay, so that's the lemma. So let's take that lemma with us down there and see. Yeah, I just forgot. We need this type to be as general as the one down there to be able to use it, to be able to use the lemma. So, okay, so that is done. Okay. So now let us start with exercise number 2. Yeah, but before I go to the exercise number 2, I just would like to elaborate a little on the counterexample found here because I think I didn't adequately explain it. So that should be a tree, not tree again. I just want to make the counterexample more readable. Okay, so here we have this tree. So we have a tree like that. So we have a tree that just has root as with 1, and when we're looking for has a 0, and then we're looking for a 1. Okay, so basically we have is in 2 that I will just call this t. So t some 1, and then looking for 1. Okay, and then when you're doing the comparison here, you will find it's not less than 0. 1 is not less than 0, so you will go to the right, and the right is a leaf. But before you go to the right, you will change, like when you move there, it will become is in 2 of a leaf and some 0 and 1, and then you're at the leaf. When you're at the leaf with and then doing this comparison, you'll find that you will return false. Okay, even though those two are equal. Okay, so what that means is, okay, is in 2 return a false, but the right hand side of the equality here is true because this second disjunct is still true. Okay, that's why we want to make sure that we had this assumption that I added earlier, which I got from the down there, which is that the postponed comparison is always smaller than every member in the given tree, strictly smaller than every member in the given tree. So that's why, yeah, we have that assumption. Okay, so now let's go to exercise number 2. So what in exercise number 2 we want to implement a high preserving in-order join. And what that means is that you want a function that takes 2 trees and creates a new tree out of them, and that tree has the members of all of the given has all the members of the given two trees. That's number one. And number two, it's the height of the newly formed tree, or the joining of the two trees, should be at most one more than the heights of either one of the given trees. And those two properties are represented by those two lemmas. Okay. So I will graphically again explain how join operates. Okay, and that is usually how I would come up with a recursive definition. Firstly, we'll visualize it. At least that's how I work. So 1, 2, 3. This is a tree, for example. Okay, and then another tree is 4, 5, and 6. And then if you want to join those two trees, what you would do, what that means basically is that you want to join them at the right, at the maximum point of the first tree and the minimum point of the second tree. So you basically want to create a new tree whose root is one of those, either the maximum of that or the minimum of that. Okay, and then that root should basically be something. So in this case, I'll just choose the maximum of that of the left one. So in this, so the root will be 3, and then I want all the orders. And I want to preserve the order, so I basically want all the members of T1, the first tree, to be on the left, and all the members of this one to be on the right. So the way I would do that is recursively is by traversing both of those spines. So the right spine of the left tree and the left spine of the right tree, and I recursively traverse both of them until I reach basically the end of each of them. And once I reach the end of them, I start reconstructing a tree which is rooted at one of the two ends. And here I'll just choose the left one. That will be the root. Okay. So here in this case, okay, you would first join would start there, and there, and then we do a recursive call here and there. And then we'll do another recursive call here and there, and then it will discover that it's a leaf. And then when it discovers it's a leaf, we go up, and then we start a new tree, whose root is 3. And as its right subtree will be the subtree whose root is 4. And then the right subtree of 4 will just stay as it was. I'll just call this R, then call this R as well. Okay. Alright, and then this will be, I'll just call this L. Okay, and this will be L. Okay, so that's the first thing. And then you want to integrate both trees in this tree when you're going up back in your recursive call. Okay, so the next stage is basically we want to add this and that to this tree. Okay, and we're going up. So the way you would do that, you would get the 3, okay, and then a left subtree of it would be one whose root is 2. Okay, that's the only way it makes sense given that we need ordering. Okay, but then root has a right child who's 3. That would be replaced with the left subtree of 3. So the right subtree of 2 would be just L, and then the left subtree of 2 would be as it was, and the same for that. Okay, so the only way it would make sense for us to integrate this tree with that, keeping the ordering, is to have 5, either to have 5 as the right subtree of 4, but then in this case you're risking increasing the height too much. Or, so let me just show you that first wrong scenario, and then I'll show you the correct one. So if one way to preserve the ordering is to just do that, okay, and then put 5 there, and then 6, and then give this, give the left subtree of 5 and replace 4 with R, okay, So here we have our height. So what's the height of the right side? 1, 2, 3. 1, 2, 3, 4. Okay, and the right, this is 4. But the given heights of the heights of the given two trees was only 2. So here we're violating the height constraint. So we cannot do this. So another way to do this, another way to do join the right tree as well, is instead of leaving the 4 as it was, no, you would do a rotation. So instead of the 4, you would have the 5 actually, and then the left subtree of the 5 would again become 4. Okay, and the right subtree of 4 stays as it was, and the right subtree of 5 would be as it was. Okay. So now I will write a recursive definition that does these transformations. So let me do that. So the function is called join, that's the signature. Okay. Okay, so as I was saying, we will be recursing down those two spines. So we'll be doing recursion on the given two trees. So it takes the two trees. So the first pattern that I will be matching against is when the second one is a leaf. Okay, and in this case, you will just return the left one, and the same for the right one when it's a leaf. Okay. The more interesting case is when both of them have data in them. So L1, A1, R1, and this, and L2, A2, R2. So what we have here is so we will do a recursive call that descends along the two spines. So it is like so R1 and L2. So the two spines that we're talking about. But if we just continue doing that, we will, like, if we just leave it at that, what the function will return to us is like, so for example, if you finish, if the left spine is longer, it will return to us, sorry, if the left spine is shorter, so if we have a leaf here but we have still some more there, it will just return to us this tree, this subtree. So what we need to do is now to define how will these transformations that I just wrote be done functionally. Okay. So we have two cases. The first one is when if the join is a leaf, and in this case, this is basically equivalent to the case when we reach the leaf there and the leaf there. So we would reconstruct that tree, and the way we would do that is, so here the A1 is equivalent to the 3 and the A2 is equivalent to the 4, so we would construct a tree whose left subtree is the left subtree of A1, or which is equivalent to this L, and whose root is A1, which is equivalent to 3, and whose right subtree is a subtree whose left subtree is a leaf like this one, which because we have reached the end there as well, and whose right subtree is the right subtree of 4 or of A2 here in this case, and whose root is A2. Okay, and this needs to be parenthesized. Okay, so this one case, which is equivalent to that. Then when you're doing the integration up there, it will work as follows. So you have so we have L, A, R. Okay. So here the L and A and the R. So the L is equal to the 3. Sorry, the A is equal to the 3. The L is this one, and the R is that whole thing. Okay. So what we will do is exactly what I did in the figure, which is to create a new subtree, a new tree, whose root is again the 3, which is the A in our case. So node some left subtree and A and some right subtree. Okay, and the left subtree of that tree will just be the tree whose root is 2, which is equivalent here to A1. So in the case, so another node, and whose root is A1, and the left subtree is the same, so L1, A1, and whose right subtree is the left subtree of the 3. So here, or of the return tree from the join, so it's L. Okay, and similarly for the other side, we get a right subtree that inherits the elements in the way we did it here. So you get 5 to get to be your right, the root of your right subtree, and then its left subtree becomes your right subtree. Okay, which is that. Okay, so I will just try this function quickly on the tree that I drew in the paper. So let's just say node. The first tree was 1, 2, 3. So one and another and 2 and 3. That's the first tree, and the second tree is 4 and 5 and 6. Okay, and then I will be joining both of those trees. And the result is a tree as we expected it, whose root is 3, and whose left subtree is the 1 and 2, and whose right subtree is the 4, 5, and 6. Okay, so you can also, there's also another alternative definition where instead of taking where instead of making this one the root, you could also make this the 4 the root, and then I recommend you just exercise and try that one by yourself. So now we have to prove the two properties of that joint function. The first one is that okay, so okay, so because this function is not a structure, a primitive recursion function, so we cannot do structural induction. Instead, we will do the computational induction using the induction principle that came with defining join. So rule join induct and then go to. So what happens? Okay, so here we have that case statement, and we need to do a case split. And what that means, let me just show you quickly. So theorem. So with every data type you create, you get a split theorem that handles case statements over that type. So in this case, we're talking about trees. So tree that splits, and that is the case split. So here we have, so what that says basically is that if you have a predicate that applies to a case statement over trees, that is exactly equivalent to that, to the predicate, to this conjunction. And so basically, if a predicate applies to F1 if the tree is empty, or if it's a leaf, then we have that, the equivalent part to this first of the case statement. And the equivalent part to that is to say for any left subtree, right subtree, and root, if our tree is is considered of those three components, then the predicate has to apply to F2 of those those three components. Okay, so it basically splits our goal into as many sub goals as there are constructors for the type here in this case. So, and the way you do the splitting is by saying tree splits. Okay, and then it's done. The second lemma is to show that the height is at most one more again. I know we'll just do the same induction. Okay, and then apply O2. Okay, so we need again the split. Okay, and then it does it also. Okay, so again, you can just do that. Kind of interesting. It's a different syntax, so you can always remove a one-step proof by just saying by. Okay. All right. So the third exercise is about implementing delete. So it's a function that takes a tree and an element and deletes that element if it exists in the tree, and then reconstructs the tree so that it preserves the order is preserved. Okay. So one way to do that is by join. So let me just show you how that would work. So we have the tree 1, 2, 3. Let's say we want to delete 2 from here. Okay, and I'll just say that these are actually bigger subtrees. Okay, if we want to delete the 2 from this tree, which is the root, what we want to do is to create a new tree that has almost the same height of the given tree or less. So we don't want to destroy the balancedness of the tree, and at the same time it has the same order. Okay, the way you can do that is by basically joining the left subtree and the right subtree together, and from the definition of join, as I showed you, it will just create a new tree with the elements of just those, the left and the right subtrees, with the right heights and the correct balancedness, but without 2. So okay, so I'll quickly write to you the implementation, but the more interesting part here is the proof, but I will just quickly show you how to implement that function. So and again, it's using join. Okay, so delete and an alpha, and returns a tree. where, so if you're deleting from a leaf, then you are going to get the same leaf. Okay. And if you're deleting from a tree with, let me just follow the signature actually in the sheet because I think I made a mistake there. Yeah. So we get the member that we want to delete first before the tree. Okay. Right. And if you want to delete an actual tree, delete from a tree with members in it, then you have node LAR. Okay, and then in this case we do the following. So we can do an if then else. If x equals a, then I will do what I just did here in the figure. So you will join the left and the right subtrees. Otherwise, if x is strictly less than a, then you will just delete it from the left subtree. And make that the left subtree of the given tree. Okay. And A and R. Else you will delete it from the right subtree. And this needs to be parenthesized. Yeah, because this needs to be a linear order in order for it to have a comparison operator. Okay, and this should be L and the right one. Okay, so that is deletion. So now let's go to the more interesting part, which is proving that. So what we want to prove about this delete function is that basically, if you delete something from a tree, you will have the same. You'll have the tree. The members of the tree will not have that thing that you have deleted, which is this lemma, and which is this lemma, and that the new tree will be a binary search tree as well. So to preserve its orderness. Okay. So the proof. In order for us to prove that, we would need to firstly prove some properties about join. Okay, so the strategy is as follows. So I'm trying to give you the strategy because it will help you if you follow it in your homework as well. If we want to prove some lemmas about join that that make us not care about the implementation details about join. So basically, we want to prove lemmas about the properties that we care about from join. Okay. So the first such property is, I think it was already. So it is this one. So just make that clearer. So the first such property is this one. Okay. So if the member, so firstly, when you define a new data type, you get a function called set. So for example, here for data type tree, we got a function called set tree. Okay. So we want to prove that the join function preserves those preserve the elements of both joined trees, so as in the elements of the joined trees is the same as the union of the elements of the two given trees. Okay. And one way to do that is by reasoning about by using. So one way to reason about these sets is by reasoning about the set of members in an in-order traversal. So this also is a good strategy to reason about sets of elements in a tree. So you reason about the set of elements in an in-order traversal. So in particular, there is this lemma here. Okay. That connects the set of elements in a given tree and the set of elements in an in-order traversal of a given tree. Okay, so this function gives you the set of elements in a list, and this function is one that gives you the set of elements in a tree. So what we want to do here is to basically transform this statement into statements about the in-order traversals of T1 and T2. Okay, so instead of set tree, we want to have we want to use that rewrite rule. Okay, so here we have if we give this to auto, it will write any set tree into a set in order of T. Okay, so what we want to do as a first step is apply auto sim with that lemma there. Okay, but okay, so that should just translate everything into the statement into a statement about in-order traversals. But there is a problem that we already have this lemma added in the sim set in the other direction. So here, notice I've added symmetric because I want to change things from set tree into set that takes a list. And we already have in the sim set, it was declared as sim the other direction, from a set of list, from set that takes a list to rewriting to the set that takes a tree. So that's why the auto is not terminating there, because we have both directions, so it keeps going back and forth between rewriting with the symmetric label, the two versions of the thing. So what I will do is just delete the original one from the sim set, and now it works. Okay, so now we rewrote everything into in-order traversals. Okay, and the second thing we want to use, okay, so now this might not be quite visible but from here, but the second lemma we would like to use on that is the one that we proved there. So we can either just copy and paste it like that. Okay, so that lemma, let me just clarify how this proof would work. So we want this will be translated into set of in-order traversal of the joined trees. And this will also be translated into a union of sets of in-order traversals. We have in the library a lemma that says, I think it's called set append. Yeah, that says that the set of elements in two appended lists is the union. Okay, so what happens here is that this lemma transforms this left-hand side into the set of in order of join T1 and T2, and then if we add this lemma, it will translate the set. It will transform that thing into a set of two appended lists, and then we have from this lemma that is already in the simp set that a set of two appended lists is the union, and then you will get the two sides will match. Okay, so you can do that because this is a one-step proof. You can also just do that. Okay, so that is the first step. Second, so now, so that's the first property of join that we care about. Okay, the second property of join is that it preserves the ordering. Okay. Okay, so this says it preserves the elements, and then we want to say that it preserves the ordering. And here I just want to show you. Again, a good strategy about reasoning about whether something is whether something. So firstly, BST is a predicate that says some tree is a binary search tree, and it's defined using this higher order predicate. So it takes another predicate there and then says. But you can look into this into detail like later on. But it basically says that it takes this takes a binary predicate that should be equivalent to some comparison operator on the elements of the tree, and then it says that this tree is ordered with respect to that comparison operator. So here BST is ordered with respect to the strictly less than operator, which means that all the elements of the left subtree are ordered with that. Sorry, the left subtree is ordered with that, and the right subtree is ordered with respect to that to less than, as in, and all the elements of the left subtree are smaller than the root, and for the right subtree they're greater than the root. Okay, so in order for you to reason about that, it usually is easier to again reason about the in-order traversal of the given tree instead of talking about whether it's a binary search tree or not. And there is this. So let me just show you firstly. Yeah. So this one. So this one here says. This one here says the equivalent shows you the equivalence between a BST and the sortedness of its in-order traversal. Okay, so again, as I was doing here, we want to translate this statement into statement about sorted lists, sorted in-order lists, in-order traversals. So and then we also want to use this lemma, which states that an appending of two lists is sorted if each of the two lists is sorted and the members of the second list are related with P to the members of the first list, which in our case will be just greater than. So the members of the second list are greater than the second, are greater than or equal to the members of the first list. Okay. So let me try and prove that. So firstly, I want to translate this statement into a statement sorted in order traversal lists. Okay. So this one BST was translating into that. Okay. That's number one. And then I want to change this thing into the in-order traversal of L appended with the in-order traversal of R. So goes like this. Okay, so now we have this and that and that, and now, and don't forget that we have this lemma that would break down a goal on the sortedness of an appended two lists into these three sub-goals, which we already have there. So this is the first sub-goal, this is the second sub-goal, and which one is the third sub-goal? Both of those basically represent the third sub-goal. So I'll just add that there and see what happens. Okay. So it's not what I wanted it to be. So I think I want to go back there. So I think that we don't want so I don't want this breaking down of the sort with respect to definition there, so I will delete that. So we have that. We need to break that down as well, and that can be done with this lemma, which, as I was saying, it breaks down a sortedness sub-goal into smaller sub-goals. So let's see. Okay. So now what we have is so let me just try and do it with the simplify without auto. No, that's not it. So there's something broken there, and I cannot tell what it is. So join in order. Okay, let me just go back there. Okay, one step again. What is this? This is not what I want. Okay, so I want to. So here, it's okay. It broke down that term into these three expressions that I don't want. And that is because it implied the okay, what I want to do is to say, instead of BST of node L XR, I want to say sorted of the in order traversal of the whole thing. I don't want it to be broken down into three parts like that. And the reason it's broken down into three parts is that it writes it does this. It automatically unfolds that definition because it has it in the sim set. So I don't want that to happen, and because I want to have a sortedness with respect to this appended list. Okay, and now I can say I want to firstly break this down into an order of the appended an appending of the in order of the left and the right tree. So we get this lemma there. Okay, so now we have that, and then the last thing is that we want to transform both of those appended in order sortedness statements into the smaller components. So basically, if we say this, so this will say that the in order of L is sorted and the in order of R is sorted, and everything in R is greater than L, and the same, and if we use that lemma, it will also break down the conclusion into the same thing. So let me see. Yeah, does it for us. Okay, so here, like the main tricks were we wanted to know. We wanted to when we were reasoning about BST, we instead it's easier to reason about the sortedness of the in-order traversals, because we already have in the library a lot of theorems about lists and the relationship, like for example this one. We have also another one that will say, so let me just do one thing back. So if we actually apply this lemma to that hypothesis, what we will get is that this is sorted and the whole thing here is sorted, and everything in that whole thing is greater than that. Notice that this highlighted thing is different from the in order of R, but because in the library we have sim rules that will tell us if this thing is sorted, then if a head and a tail is sorted, then the tail is sorted. We will be able to get that, and it also tells us that if a head and a tail, if everything in a head and a tail is greater than something, then everything in the tail is greater than the thing, which will give us the second requirement there. So that's it for that. So now now we have, I think, the proper theorems to reason about delete. So now the first lemma from that is to show that everything in the deleted number doesn't exist in the given tree. Okay. And then since delete is defined as a primitive recursion function on the given tree, we can just do the induction on tree and then apply O2. Yeah, that's it. And the second lemma, so here notice, I mean, if I remove that, let me just remove that. Let's see what happens here. So remove that as well. Yeah. So we're using this fact that the set of, like, in order for this theorem to pass, we need this. So let me just call this set tree joined. We need this lemma to prove that here, because first of all, you need, like, in order for us to prove that theorem about delete, we don't really need any unfolding of the definition of join. We just need the lemmas about it. So that's why I will declare join sims as deleted from the sim set. Okay. We don't need any unfolding of the join. Instead, we just need the properties of join. Okay. So that's the. I mean, in this case, I don't know if it makes a difference, but in general, that's how you do it. If you think you have proven the properties of a sub-function or an auxiliary function, then you know, and you don't need to unfold the definition of the auxiliary function. You only need to reason about it with the properties that you proved. Then you can delete it from the sim set. Okay. So the proof here goes by. So let me just try and unfold that logic for us here. So this is the induction hypothesis there. So basically here we have that this is that if the left subtree is BST, then the set of elements in it are equal is that set, and the same for the right subtree. And we want to do that for the deletion. Okay, so in both cases, when you go to the left or to the right, both of those cases will be handled with the induction hypothesis. But the only problematic case will be the third case, where you have where both are equal, and then this thing will be replaced by join of T1 and T2, and that's it. And then in this case, in this case, we will need to reason about the set of elements in a join, and that's why we will have set tree of join T1 and T2 equals the union of both join of the both elements. And that side will be unfolded by the simplification rules of set tree. So it will be, it's not here, but it will be the set of T1 union the single set of the root union the set of T2. And since we know in the third problematic case that x is equal to x2, we will have we will know that this set minus x is going to be just a set of elements in T1 and a set of elements in T2. So so here we have that, and let's use that proof again. Yeah. So I'll go to the second lemma, which talks about the fact that delete preserves the ordering. And let us see what that means. So we'll apply induction here on the tree, and then what do we have there? Yeah, again, so this will hand like both when you go to the left and to the right will both be handled by the induction hypothesis, but when you're in the middle and you get a join, you will need something, this lemma about join, that says that it preserves balancedness, which is the third problematic case. Okay, so apply auto sim. Yeah, that's it. So that's it for the exercise for today. I hope you enjoyed it. Thanks for listening.